Hello class, me again, Professor Pat. Today we're going to be talking about Riemann sums, definite integrals. So let's recap what we know chapter 4 so far. First thing was indefinite integrals, which is just your antiderivative. We also learned summation using sigma notation, just a recap of the summation rules over here. We also learned how to approximate the area of a plane region. And then we learned how to find the area of a plane region using limits. Alright, so let's consider this function f of x. Let's find the area. We want to consider the region bounded by the graph, f of x equals x squared, the x-axis, and the vertical lines x equals 0 and x equals 1. So how do we find the limit of the sum of n terms for that function times the width of each function, as n approaches infinity? So we're going to go ci is our right endpoint given by the function given by I squared over n squared. And dxi, or delta xi, is going to be the width of the ith subinterval, right? So the left endpoint of the ith subinterval is going to be I minus 1 squared over n squared. So the width of each interval, dxi, is going to be equal to I squared over n squared minus I minus 1 squared over n squared, which will simplify to dxi equals 2I minus 1 over n squared. So we know that the area underneath this curve is going to be the limit as n approaches infinity of the sum of n terms of our function times our width of each subinterval. So we know that the area will be the limit. We could plug in f of c of I. We know ci is going to be equal to I squared over n squared. F of x equals square root of x. So we've got our square root of I squared over n squared times 2I minus 1 over n squared, which is our dxi. So we can factor out our 1 over n cubed to get the sum of n terms, well, the limit as n approaches infinity of 1 over n cubed times the sum of n terms starting at I equals 1 of the function 2I squared minus I. Using our rules, we'll get the limit as n approaches infinity of 4n cubed plus 3n squared minus n over 6n cubed is just going to give us 2/3. I found that using algebra. Alright, so a Riemann sum can be defined as a function f. If a function f is defined on a closed interval ab, we let our delta be our partition of ab, given by, we've got our a is equal to x sub 0, will be our starting point, which will be less than x sub 1, which will be less than x sub 2, which will so on and so forth be less than x sub n minus 1, which will be less than x sub n, which will be equal to b. Where dxi is the delta xi is going to be the width of the ith subinterval. So if c sub I is any point on the ith subinterval, then the sum of n terms, starting with 1, of f of ci times the width delta xi is considered a Riemann sum of the partition delta. It seems confusing. So partition is the width of the largest partition. The width of the largest partition is called the norm, and it's denoted by this fancy guy right here. Looks like you're taking the absolute value of your delta. Partition's considered regular when your norm, when all of your partitions and all the subintervals in the partition are of equal length, and it's denoted by your norm equals your delta x, which, as we know from earlier in chapter 4, delta x is going to be b minus a over n. So the norm is inversely related to the number of subintervals by the inequality n will be greater than or equal to b minus a divided by the norm. So as the number of subintervals in a partition approaches infinity, the width of the norm approaches 0. So as that would imply that as the norm approaches 0, n approaches infinity. So to say that the limit L, the limit exists, means that there's a real number L such that for each epsilon greater than 0, there exists a delta greater than 0, such that for each partition where the norm is greater than delta, then the absolute value of L, the value of your limit, minus your function, the sum of n terms, is going to be less than your value of epsilon, regardless of your choice of C sub I in the I subinterval of each partition. It doesn't matter what you choose. The value of the limit minus the function that you're limiting, the absolute value of that is always going to be less than your epsilon. So, what is the definition of a definite integral? Well, if f is defined on the closed interval AB and L, the limit of the Riemann sums over the partitions delta exists, then f is said to be integrable on closed interval AB, and the limit is denoted by, you see your limit as your norm approaches 0 of the sum of n terms, starting with 1, of your function times your width is going to be equal to the definite integral of f from A to B. A is your lower limit of integration, and B will be your upper limit of integration. So theorem 4.4 states, if f is continuous on a closed interval AB, then f is integrable on the closed interval AB. Therefore, the definite integral of f from A to B exists. So we want to find the integral of 2x from -2 to 1. First thing we'll do is write that in our other notation. We know that the integral can be rewritten as the sum, as the limit as the norm approaches 0 of the sum of n terms. And if you'll recall, the norm approaching 0 implies that n is approaching infinity, so we can rewrite that one step further to get the limit as n approaches infinity of the sum of n terms of your function times your width. Where 2x would be f of x, dxi is your width, your b minus a, your 1 minus -2, your 3 over n is your dx. So we'll use ci, we'll use a plus I dx, delta x, to get our value of ci. So we get -2 plus 3i over n. I chose to rewrite it as 3i over n minus 2. Alright, so using our summation notation skills, I was able to factor this down, reduce it, simplify to get our value of this integral of 2x from -2 to 1 is going to be equal to -3. So if you look on the graph, we'll notice that even without looking on the graph, you notice that that integral is negative. So because it's negative, that integral cannot represent an area. So definite integrals can be positive, negative, or 0. But in order for a definite integral to be considered, to be interpreted as an area, a function f must be continuous and non-negative on your closed interval AB. So theorem 4.5 states, if a function f is continuous and non-negative on the closed interval AB, then the area of the region bounded by the graph of f of x, the x-axis, and the two vertical lines x equals a and x equals b, will have your area equals the definite integral of f of x from a to b. Boom. So let's try to find a definite integral of f of x equals 4x minus x squared from 0 to 4. These are two different ways to write the same thing. So we know our area is going to be equal to the limit of f of x, not the limit, excuse me. Our area is going to be equal to the integral of f of x from a to b. We know that's our limit as our norm approaches 0 of the sum of n terms of our function times our width, which we know can be rewritten as the limit as n approaches infinity of the sum of n terms of our function times our width. So we've got our dxi is going to be equal to dx. It'll just be b minus a over n, which will just be 4 over n. And our ci is going to be a plus I dx. So 0 plus I times 4 over n is just going to be 4i over n. So we've got our limit as n approaches infinity of the sum of n terms of fci dxi will be the limit as n approaches infinity of the sum of n terms of f 4i over n times 4i over n. We can remove that 4 over n to get I put that on the wrong side here, but our area should be the limit as n approaches infinity of 4 over n times the sum of n terms of 4 times 4i over n minus 4i over n squared. If you're not sure where that's coming from, that's our function. I took f of c of I and I input our value of c of I into this function. Up here, here's our graph of this function. Continuing with my algebra, I get the limit to be equal to 32 over 3. Not sure what's going on behind me. I was able to find these using basic algebra and our rules for sigma notation. Alright, so some properties of definite integrals. If f is defined at x equals a, then the integral of f from a to a is going to be 0. If f is integrable on the closed interval ab, then the integral of f from b to a is the opposite of the integral of f from a to b. Theorem 4.6 states if the function f is integrable on 3 closed intervals determined by a, b, and c, then the integral of f from a to b is going to be equal to the integral of f from a to c plus the integral of f from c to b. This is a really good visualization of Theorem 4.6. Theorem 4.7 states that if f and g are integrable on the closed interval ab and k is a constant, kf will be integrable as the integral of kf from a to b is going to be equal to k times the integral of f from a to b. If f plus g is integrable, as the integral of f plus g from a to b is going to be the integral of f from a to b plus the integral of g from a to b. It makes sense. Theorem 4.8 states if a function f is integrable and non-negative on a to b, then it will always be greater than or equal to 0. If the function f and g are integrable on the closed interval ab and f of x is less than or equal to g of x for every x in the closed interval ab, then the integral of f from a to b will be less than or equal to the integral of g from a to b, always. Any questions?